Our next example is not actually a linear equation. Okay? So why is it in this section? Well, I can use the same techniques as the previous example and multiply through by common denominators to get rid of the fractions, and it will actually create a linear equation, is why we're covering it in this section. We can solve it with the same techniques. It's actually a rational equation because I have the fractions with x on the bottom. But I can solve it, as I said, in the same method. I look through at the denominators. I've got an x minus 2, and an x times x minus 2. Well, if I use the product, x times x minus 2, that would be a common multiple of all of these that they'll all divide into. So I have to multiply every single term by x times x minus 2, which is a pretty long string here to write down, but you need to do that, okay? Oh, and the note here, this is very important on this example. We can sometimes get what are called extraneous solutions, and we actually will on this problem. If we happen to get x equals 0 or x equals 2, those cannot be solutions because they're not in the domain. If you look at the left-hand side, the right-hand side, on the left-hand side, my domain would be x can't be 0, x can't be 2, all real numbers except 0 and 2. On the right-hand side, x can't be 2. So we can't have x equals 0 or 2 because when we plug those in, we would have undefined statements. Okay. But now we're going to multiply through by x times x minus 2, and we get, as I say, this long string here, this long expression. But I highly recommend you don't try to cancel in your head, because if you do, you're probably going to make a mistake. I know I would. Okay, so I'm going to write it all out. I'm going to get x times x minus 2, my common denominator, times the first term, 10 over x times x minus 2. Plus, I have 4 over x times x minus 2 is equal to x times x minus 2 times the left-hand side, 5 over x minus 2. And then in each of those, I get some cancellation. Okay? In my first term, I have an x times x minus 2, and then on the bottom, we have an x times x minus 2. They're both going to cancel and just leave me with 10. In the second piece, we can cancel the x's, and then on the other side, we can cancel the x minus 2's. So if you look at it, that's going to leave you with just 10 for the first term, and then you have 4 times x minus 2, and then equals 5 times x would be what's left if we cancel. And I'll point out what we're doing there is we're using the identity property. If x is not equal to 0 or 2, then x times x minus 2 divided by x times x minus 2 is equal to 1, and then we have 1 times 10 is 10. If x is not equal to 0, x divided by x is 1, and we get 1 times x minus 2 times 4 is 4 times x minus 2, and so forth there. We did just assume when we did the cancellation, this is really important in the end, we just assumed that x was not 0 or 2. Remember that, okay? So we got 10 plus 4 times x minus 2 equals 5x. Now we have a linear equation. We can distribute the 4. We get 10 plus 4x minus 8, if we distribute the 4, is equal to 5x. Combine the like terms. 10 minus 8 will give me 2, plus 4x equals 5x. Subtract 4x from both sides, and we get 2 is equal to x. Okay? So we found this solution, x equals 2, but as I just said, we assumed x was not 2 because that gives division by 0. This is what we call an extraneous solution. Sometimes, it doesn't always happen, but sometimes we get no solution for this type of problem. When we did the work correctly, the value we found that solved the linear equation is x equals 2, but I can't plug that into the original equation because I would divide by 0. Whenever you create an answer along the way that doesn't work in the original problem, we call that extraneous. There's a few places in algebra that this happens, and this is one of them. When I cancel a variable from the denominator, I might be creating an extraneous solution. Okay. So this problem, we had to do a lot to work to figure out it has no solution. Okay. Next up, we're going to talk about literal equations or formulas. Okay, so a literal equation has letters in it, multiple letters. We use these all the time in math and science. I have some on the screen there. We got Einstein's relativity, E equals mc squared. The ideal gas law from chemistries, pressure times volume equals nRT. The area of a rectangle is length times width. So we see these things all over the place, okay? And it's really important to be able to manipulate them and solve for particular variables. That's what we're talking about here. And we use the same techniques as solving equations that we talked about before. It's just we have to treat the extra letters as constants, okay? So a simple but very useful example is temperature. We have multiple ways of measuring temperature. Probably the two most common are Fahrenheit and Celsius, right? In the US, if I say it's 80 degrees today, we're talking about 80 degrees Fahrenheit. A lot of other countries use Celsius. In science, often we use Celsius because it's a 100-point scale where water freezes at 0 and boils at 100. So you might have a thermometer that you've used in your science class and found that, say, something is 20 degrees Celsius and you want to know Fahrenheit. Well, you could plug into this formula. The Fahrenheit temperature would be 32 plus 1.5 times C, okay, times the Celsius temperature. Or you might have a Fahrenheit thermometer but be in your chemistry class and you need to convert it to Celsius. If you did, instead of doing that conversion every time, it would be nice to solve this equation for C instead. Okay? And I'll point out, to connect to a previous section, we're actually finding the inverse function when we do that, just in context here. But anyway, we have a literal equation which has multiple letters, this time 2, and we want to solve for one of them. So to solve for it means I need C by itself and an expression on the other side that doesn't involve C. You just have to treat F like a constant. Okay? I would subtract 32 from both sides. I don't know what F is in general, so I get F minus 32 is equal to 1.8 times C. Divide both sides by 1.8, and there we go. If we don't mind having the complex fraction with the decimal on the bottom, and this would be perfectly usable, right, in science, we have F minus 32 all divided by 1.8 would give us the Celsius temperature. So that's what we mean by solving a literal equation. I've got C by itself and an expression on the other side involving numbers and operations and the other variable or variables, in this case, F. Here's another example. A book I used one time pointed this one out as an example. A lot of students might just want to subtract and say that A minus PRT equals P is solved for P. It would not be, because you would have P on both sides. This one, you have to factor P out first. Okay? If we want to solve for P, we've got A equals P plus PRT, which happens to be a compound interest formula we'll talk about later in Chapter 4. But you can factor P out, use the distributive property in reverse, right? And we need a 1 there. We're dividing this by P, basically. So if we were to go backwards, we'd have P times 1 is P plus P times RT. Okay? So P plus PRT can be rewritten as P times the quantity 1 plus RT. And then it's P times all that, and I can just divide the whole thing and get A divided by 1 plus RT is P. Okay? So it can get pretty complicated depending on the equations that you have to solve, but to solve for a variable means that you have to isolate it by itself on one side so that you have a formula involving the other variables that it's related to. And this is extremely useful in the real world when we have formulas that tell us real world applications.